So I'm going to give you an architecture talk, but the first thing is we're delighted to announce the Turing Award. This year's Turing Award is going to what I consider the three musketeers of deep neural networks. So if you don't remember the three musketeers, it was all for one, one for all. And they really conspired together during the neural net winter and figured out how to. They never gave up the faith. They stuck with it despite no one believing in them and re-engineered the resurgence of deep neural networks. And the AM Turing Award was announced today. So the most senior member is Jeff Hinton. Jan LeCun was one of his postdocs, and Joshua Benchio worked for Jan LeCun at Bell Labs, but they collaborated over the years. But Hinton's the most senior one. He's the same age I am. So what was the reward for Hinton? Well, the $1 million prize had to be split three ways. So Hinton got the extra penny for the seniority. But they all wrote letters for each other for the award, and they're pals, and they kind of conspired together in Canada to bring about this revolution that we're all enjoying. So my talk today is based on two talks. I work for Google now instead of just the university, and so I'm limited to talking about things that have already been talked about. So how did we get here? Kind of shockingly, the end of general purpose microprocessor performance. This is the first figure from Hennessy's in my textbook. It's in the 6th edition now. Every year we add the speed up, and there were the good old days in the 1980s, 1990s, early 2000s, and the RISC era, where performance doubled every 18 months. So the thing that people thought was Moore's law, we turned into performance every 18 months. And for those who weren't around then, what that meant was you would have a perfectly good computer, and then your neighbor, your friend, would get a newer computer, and you'd be jealous because it'd be 3 times faster than your computer. So you'd throw away your perfectly good working computer to buy a new one so that you could get your work done as well as the other person. So these days, what's happened is, the end of Dennard scaling, the end of Moore's law, with the multi-core switch, there's this Amdahl's law that limits to it. And now, when do you throw your laptop away? I just got a new laptop. Why did I throw it away? It broke. The old one stopped working. I had no choice. I had to buy a new one, but I didn't buy it for performance. So we're in this really difficult era now where our software colleagues are used to getting this giant jump in performance. It was the phrase, what Moore's law giveth, or what Moore giveth, Gates taketh away, right? If the software people would suck up all those cycles, hopefully to provide important new functionality. But they're used to that, and this underlying acceleration is gone. So transistors are still getting better, just not at the rate of Moore's law, and they're not getting that much better. The power budget, for air-cooled devices isn't getting much higher. We've already done the switch in the early 2000s from 1 processor per switch, so the software didn't have to worry about it, to many cores per switch. You can do that trick once. As far as people like computer architects like Bill Daly and I, as far as we know, the only path left is domain-specific architectures, as far as we know. So that'll do a narrow class of things well. You can make big jumps in that, but we don't know how to make general-purpose computers run faster. So this is going to be a big change, societal change. So from a computer architecture perspective, the ideas of neural networks that we need to know about is training or learning versus inference or serving the results. So you develop the model, and that takes lots of cycles to do that. And then once you've got it working, you serve it, and that's called inference. There's this idea of batch size. You want to amortize the training that you're doing. That you get these weights of parameters, and you don't want to fetch them every time you get a new sample. You'd like to collect a lot of samples together and train them together. That's the batch size. And then we'll talk some about doing things in floating point or doing it in integer, and machine learning people call that deep quantization. OK, so how did Google get into this? So Google probably got into this earlier than most companies, I think. I think we can say that historically now. So in 2013, because Google was kind of early into machine learning, it actually got into it. Jeff Dean led the BRAIN group. And it was before this ImageNet competition that Jeff Hinton won that was part of the reason that he got the Turing Award. So they got involved before it. So they were already speculating that machine learning might work. Oh my God, what happens if machine learning works? And so they did this, I think Jeff Dean did this calculation. Suppose all of the Android users use their phones 3 minutes a day to do some language translation using their phones. Well, the calculation of using standard general purpose Intel servers was Google would have to double or triple the size of its data centers to handle that load, which would be unaffordable. So that looked like a kind of success disaster in the future. So they started an emergency project, like a Manhattan project. They get this done as fast as possible. And you're going to do the serving or inference. You got to do 10 times better than CPUs. That's the goal. You got to do 10 times better than CPU to make this affordable. Maybe Google could afford to increase in the demand its data centers by 10%, but not by factors of 2 or 3. So it started in 2014, and amazingly enough, the people who did this put this into data centers and started working 15 months after the project started, which is remarkable for custom silicon. And then, for reasons I don't understand, the CEO of the company in May of 2016, as part of Google's kind of annual event, said, oh, by the way, we've built our own custom hardware for neural networks that's 10, and the technical details was 10 times the performance per watt. And that was just put out there. So the reaction of the venture capital community was, oh my God, Google's doing this, and started funding an incredible number of startups. So I don't know what the strategy Google had to announce it without any details, but it led to this renaissance of hardware startups. And I heard somebody tell me recently that he thought that there were 120 hardware startups around machine learning. OK, so what is this first tensor processing unit, TPU, which we now call V1? It was for inference. It's been in production for 4 years. If you use Google, you're using TPU V1. And its most famous use was it powered the AlphaGo match, where for the first time a computer program beat a human champion at Go. It's a relatively modest card that you could stick into standard Intel servers, 4 cards per server. What's the workload? For inference workload in the data center, this was in 2016 when we wrote the paper. Kind of surprisingly, MLPs, kind of dense matrix calculations, were 60% of the load. The LSTMs that used for translate and things like that, those were about 30% of the load. And the convolutional neural networks for which Yang Kuhn won the Turing Award in the data center inference at that time for our workload was only 5%, which was a surprisingly small amount. And it gives you some ideas about the number of weights, the number of layers for these networks. Because it was an emergency project, it was done as an I/O device that plugged in over the PCI bus. And it was decided to do for the CPU to be in charge, sending instructions over the PCI bus to drive this thing like as a floating point unit. And because it was going over the I/O bus, they would be powerful instructions, CISC instructions that would last tens of cycles to make this work. Here's the block diagram of it. And the heart of the design, or the main bet of the architects, was this giant matrix multiply unit. It's an amazingly 65,000 that do 8-bit multiplies and accumulate at 24 or 32 bits, organized in a rectangle, organized in a square, 256 by 256. Since a big piece of the neural networks is this matrix multiply at the center, they decided to do that. The clock rate isn't that high at 700 megahertz, but when you multiply 65,000 times 700 megahertz by doing a multiply and add, that's 92 tera operations per second, which is pretty amazing for a 2015 chip. So many more multiply accumulate hardware than contemporary chips. And reflecting back on this, well, why was that? That's because those chips had no idea about machine learning. The GPUs and CPUs were designed a long time before this thing happened. So these are chips that were out there. GPUs became popular because they had pretty good single precision floating point performance. So it was a good match to the workload, but that was sheer serendipity. There was no plans to design it for machine learning. It just worked well. So these was designed not only to do machine learning, but do the inference part of it, which is the easier part of it. So that's plausibly why there was this opportunity in 2015 to have this big jump in performance. The other part of the design is, and you'll see this in design today, besides a multiply unit is a lot of memory on the chip, because you want to keep on the memory on the chip, both for energy reasons and for bandwidth reasons. There wasn't enough memory on the chip to be able to handle all the weights, which could be 100 megabytes. So that was done with a separate standard DRAM off the chip would hold the weights. For inference, these weights are read-only, so you'd only be reading it off the chip. And that was just the smallest amount of DRAM you could get. So that was the design, this 15-month design. A kind of a cartoon of the layout of the chip itself. You say more than half of the chip is that matrix multiply unit and the memory of it. And there's hardly any of it was controlled because it has a very powerful data path and because the CPU sent the instructions to it. What do the instructions look like? There's only a dozen of them. These are the 5 most popular. You read from the CPU host memory, you write the CPU host memory, you read the weights to do the inference, and then you do a matrix multiply or a convolution, and then you do the activation function. So there's the nonlinear piece that happens after the matrix multiply. And as I said, the average clock cycles per instruction is more than 10, and it had a simple 4-stage pipeline. But these instructions could last a long time. But the basic idea was to hide everything you could behind the matrix multiplier. And the complexity was all in the software. It didn't have to handle any branches. Everything was in order issue, so a straightforward design, primarily because of how quickly they had to get the project done. But 65,000, given that we're limited by power, 65,000 matrix multiplies every clock cycle could be tremendous power. So they brought back an idea from the 1980s that really hadn't been used very much called systolic arrays, or systolic execution. And it's systolic like blood pumping through the body. That's where the name comes from. And the idea is that if you can schedule everything perfectly, you could have matrix multiplies coming, or the inputs to the matrix multiply on one side, inputs to the matrix multiply on the other side. The partial products will get accumulated, and it's like choreographing a dance. If you set it up right, you can have everything flow without lots of register accesses. So maybe that saves a factor of 2 in power, and can also saves area compared to doing it the straightforward way. And a lot of the power of that chip is in the matrix multiply unit, so it was kind of a brilliant inspiration to bring back that idea. So for those of us who write textbooks and have this history section that you put in, and you're hoping people read them, the great thing about the Google engineers, they weren't young, they were old, and they knew the history. And so they brought ideas back that we hadn't seen for a long time, and that remains one of the key features of the TPUs. Now, like I said, Google, in its data centers at that time, had, that was the NVIDIA K80 and the CPU. Those were the chips at the time. Again, they were not designed for neural networking. This was probably the first production chip to do it. So how is this going to work? How did it look? Well, it used a lot less power than the contemporaries, about half the power. And Google doesn't want to reveal the actual die size and the actual technology. No, or the technology, so you can't figure out who its partner is. But you can say it's less than half the size of the CPU is a thing that you can say. And it just does 8-bit integer multiplies and accumulates at 32 bits, not floating point, because you can get away with it. This is what you're insert them into servers. The Haswell servers, both the K80s and the TPUs are inserted into the servers. And this shows you how much power it takes with the server. So now let's try to investigate the performance. My colleagues thought a great way to illustrate this would be to bring back an idea that I was involved in called the roofline model. And it's a bottleneck analysis. The simplifying assumption is either you're limited by your compute, your data path, or you're limited by your memory system. So how can we illustrate that visually? Sam Williams, a PhD student of mine, came up with this idea that the flat part of the, so-called the flat part of the roof would be the peak performance. And the slanted part of the roof would be the memory bandwidth. And so the y-axis is gigaflops on a log scale. And the x-axis is the number of operations per byte. So the idea is if you're not doing very many operations per byte, then you're over in the slanted part of the roof. You're limited by the memory bandwidth. And if you're doing a lot of operations per byte, then you're over in the flat part of the roof. You're limited by the peak performance. So, and then what's the operational intensity? What's the number of operations per byte? Well, that's a function of the program you're running. And so for neural networking, depending on your model, like CNNs tend to have higher operational intensity. LSTMs tend to have lower. So you'll end up somewhere in that chart. So that's kind of the basic idea. The other question from a computer architecture is where is that ridge point? Where does it bend over where you can get, how much operational intensity do you need to hit that peak performance? What do you have to do to get up there? Okay, so here's the TPU Refine. So this is a really steep roof. So remember I told you the part we used standard DDR, kind of straightforward DRAM? We had an incredibly powerful big matrix multiply unit, but standard DRAM. So what that means was almost everything's going to be memory limited. So the 6 production applications you see there, 4 of them are bumping their heads about the slanted part of the roof. That means they're memory limited. There's only 2 of them over to the right underneath the flat part of the roof. So you need a lot of operational intensity to hit the peak performance there. What about the CPUs and GPUs? Well, this is the CPU. I changed the y-axis scale, but it's much flatter. But you notice, even though they're not memory limited, they're kind of far from the roof line, and that's somewhat true of the GPU is true. It's got much higher memory bandwidth, so it's a much flatter roof. So more of them are under the computation intensity, but it's away. So that was the first thing we had to figure out. Why is that? So kind of surprisingly, to me at the time at least, was when we looked at the data was that inference is serving people, right? People go to Google and do the inference. The application people cared tremendously about response time. They gave us a hard stop deadline. If it was longer than that, we weren't going to use your chip. So it turned out to be often around 7 milliseconds. So you can see the green rows are 7 milliseconds are set, so that was the response time was good enough. And the red rows, well, you get more performance, more throughput, but you missed the deadline, so we don't care, we're not going to use it. So what it meant was, because the CPU and GPU, which were not designed for neural networks, have all these things in them that make the average case go better. So caches and branch predictors, prefetching, these are all, on average, they help. But what about the 99th response time limit? They don't help so much, right? So there was this extra hardware, and they had more potential to go much faster, but they were too slow in latency. So it was kind of the surprise is that inference is latency limited because, as you'll see, training is not. Training is throughput limited. But we were new to this, so that was a surprise. So if we put all the roof lines together, that's what it looks like. So this is incredibly high peak for the TPU, but it's got this long slanted thing. Most things are memory limited, whereas the other designs don't have that long roof, but they're away from it probably because of the response time. But that's in a log-log scale. I get confused with long-log scales. So on a linear scale, it looks like that, right? So that's how much different. That's how big 92 teraops is. So then, given we're limited by power, then what about the performance per watt? And so we calculated that 2 ways. And one is when you include the host CPU in the power, or if you just talk about the accelerators by themselves, chips by themselves. So basically, it's kind of remarkably in performance per watt was a factor of 30 or 80. Now, I told you we used the standard DDR DRAMs that you would find like in a PC. NVIDIA, sensibly enough, used graphics DDR, which is much higher bandwidth, but Google didn't have the time to get the IP to get the graphics work. From a computer architect's perspective, you kind of like, well, what would have happened if we'd used the same speed memory? And what happens, and you can see it in the roof line, if we're going to go much higher memory bandwidth, that roof line, the slanted part better go up and the ridge point move, and that's what it does. It moves it way over, so a bunch of the things were memory bound got a lot faster, and the net effect of that was it moved it up, this is hypothetically, it moved it up from, I guess, what was it, 30 to 80 to more like 70 to 200 times better. This is what the related work section. So people can't say I didn't mention the related work. Okay. So let's do the conclusion for the first part, and I'm going to have plenty of time for questions here. So I expect you to start doing them. So why did it work? I think fundamentally, as you look back, is we were starting to run in these limits where things were starting to slow down. They weren't getting better, for CPUs at least. They were starting to grind to a halt, and people, if they were starting to think about the ML workloads in 2015, that's fine, but it takes years to bring out chips. So kind of fundamentally, we were competing against general purpose devices with a special purpose thing. Like we had a race car, and they were doing family sedans or something like that. Or I don't know what the right analogy is. Bill's a car guy; he'll come up with the right analogy. But they're standard. That's kind of fundamentally, I think, the high-level thing. Now, technically, the bet was on this really large multiply unit. It didn't use caches, right? That 99% latency, caches may not have helped. It had memory that was under software control. So if you know your application well, you can use a scratchpad memory more efficiently than you're probabilistically accessing it because of caches. Because it was at the end of I/O bus, we had to run almost all the work in that CPU, which if we had been going back and forth between the CPU and TPU, we would have been I/O bus bound. So we had to have enough of the work over on the TPU for that to make sense, and we were able to do that. That's kind of fortunately, they decided to build a single-threaded model, just one core, with really simple things, with no average case optimizations, and that turned out to be a fortunate match to the 99th percentile response times that the applications insisted. So according to the people who were there at the time, I joined many years later, they went and asked the people, how big a deal is the response time? They said, it's not that bad. And most of the people didn't have a response time limit for the applications they were considering at the time. And the ones that did said 10 milliseconds, right? And then so they came back a year later with the design. And they said, oh, great. All right, the response time limit is 7 milliseconds for most of our applications. So it was good luck that they designed a simple design. And it had, if it only ran on the algorithms of 2013, like AlexNet, if it only did that well, it would have succeeded. So the people had to try and guess where machine learning was going to go and have enough support for things that weren't as popular then, like LSTMs. LSTMs were just coming on the scene, and they put in support for that. It turned out this is kind of the bet of domain-specific architectures. You leave out the stuff you don't need for that domain, and if you leave that stuff out in this limited era where you're limited by transistors and power, you could build a relatively small, certainly the die is small and relatively low power. And then for inference, it's well known you can get you don't need floating point for inference, and that was a thing to do. And when you build special purpose hardware, where's your software going to come from? Fortunately, again, this is serendipity, is our machine learning colleagues don't want to write their machine learning algorithms in C++ or C, unlike the systems people. They want it to be much more productive. So they're writing in what you could consider a domain-specific language. And examples of that are TensorFlow and PyTorch and Caffe and lots of others. And why are they doing that? They're doing that to make them more productive. The side effect of what they're doing is they're raising the level of abstraction. They're raising the level of abstraction, which is a boon to architects. Because if we were trying to take a triply nested C++ program that's doing a matrix multiply and map that by a compiler onto a systolic array, good luck. We've been trying to do that for a long time, and that's really hard to do. Instead, these languages have matrix multiply as an operation. And it's pretty easy to go from a matrix multiply in a library routine and use the matrix multiply hard. But so had they not been writing in these domain-specific languages, this wouldn't have been a success story, or we would have had to spend a lot of time porting the software. Instead, we were able to take advantage of that. So that's another serendipitous step. To me, it was surprising about this latency versus throughput, because I was just learning about it. because GPUs are so popular and so effective at training, I just thought they'd be good at inference too, but in retrospect, they weren't designed for inference, so it's not, or at least that generation wasn't designed for inference, so it's not surprising. We were, at the time, being first on the scene, we had tremendous benefits, and it's easy to see how it could have been better. And surprisingly, 15 months in this emergency to get these things in the data center, and it's factors of 10 faster, in part because of this huge amount of multiplying unit. And factors of 10 in real products are pretty rare. It's usually factors of you'd be very happy to get factors of 2, and this, because it was early, was factors of 10. Okay, so that's part 1. Part 2 is talking about co-design, and I'll talk about the more recent TPUs, what I can say about them. So the first thing is Google went for inference because it's a lot easier. Training is much harder. Training is kind of 3 times the work. You start off with this model, you initialize it with random data, you give it these input-result pairs of known good things. The first time through, it produces junk. But then you get at the end, then you do the back propagation phase, and you look at, well, what adjustments would I have had to make to the weights to get a better answer? And then you do the third phase, the weight updates. You have these little tiny numbers, usually small numbers, that you put in, and you adjust the weights, and then you do that millions of times. And kind of the magic of deep neural networks is you start off with random data, you take these known examples, you go through this millions or billions of times, and you can end up with something that's better than humans at that task. It's kind of a remarkable event. So the training jets are large. The amount of memory that you need to access is much larger. You have to communicate between the forward pass and the backward pass. You have a working set. It can be much bigger than the weights. And there's lots of opportunities to have bottlenecks. And it needs a lot more flexibility because training changes. Those algorithms change more frequently than inference. So Moore's law may be over for chips, but not for machine learning. So the first one is Moore's law for machine learning papers. So in archive, it's doubling every 18 months, the number of papers on archive and machine learning. So if you want to keep up today, I think today you'd have to read about 80 papers in archive every day to keep up with machine learning. I think that's the TensorFlow directories, or at Google, they're going up Moore's law. And then our colleagues at OpenAI, since 2012, it's a little hard to see that on the chart, plotted, if you want to be at the leading edge, the state of the art of training, how much more computation do you need every year? And they plotted it from 2012 to 2018, and they calculated doubling every 3.5 months. Remember, Moore's law used to be doubling every 18 months. So that's it's slightly more than a factor of 10 every year. So these are, if you're a computer designer, the people you hate are people say, computers are fast enough today. I don't see why you're trying to build faster computers. You love people who say, I can't get my work done. I need as much as you can build. So we love these people. Factor of 10 every year. That's ridiculous. How can you possibly deliver a factor of 10 every year? But that's what they want. If you did, they'll figure out a way to use it. And get results that end up, every month there's some result about neural networks doing something that you're surprised that they could do. But they need a lot more cycles to be able to do it. Okay, so kind of classic computer architecture, if you read our textbooks, is the hardware-software interface. That's the subtitle of our undergraduate textbook, and the instruction set's right at that interface. And what you try to do is try and cross that interface and do the easier things. Is it easier to do it in software or easier to do it in hardware? And then the synergy between them in a better system. And examples of that are very long instruction words where the compiler does most of the work, or out-of-order execution where the hardware does both the work. Both of those are trying to get instruction-level parallelism. And today, people are doing both of them. So that's kind of the classic model. What's it look like for domain-specific? Wow, there's a lot of stuff, right? Not only the hardware, but people are even investigating the physics below the digital abstraction. And then not only the compiler and the arithmetic. Who would have thought people are rethinking arithmetic? You would have thought that computer architecture in the early years was kind of computer arithmetic. But people got, that was solved long ago. Turing Awards were given for IEEE floating point. Who cares about arithmetic? Well, that's being brought up. Then there's not only the compiler, there's the libraries, algorithms changing all the time, and the models. And so some of the startups are rethinking even the physics, right? So why do computers have to be digital? Let's build analog computers. When I was a grad student, I took a course in analog computing. And that, I'm sure the course stopped shortly after I graduated. Nobody cared about analog computing. They're bringing that back. There's another old architecture bugaboo is asynchronous design. How come we have to have a clock? Why does everything have to be in the clock cycle? We're wasting all that energy and area sending that clock signal along. We should go to asynchronous computing. And then the third one, which I also was involved in as a graduate student, I was working at an aerospace company, and we actually built one of the few working what are called wafer scale computers. That is, the question is kind of the same thing. Why do we have a clock? Why are we building synchronous logic? That's stupid. The other question is you get a wafer, and it's got lots of chips on it, but for some reason we chop it into pieces, put it into packages, putting them on boards again. Well, why didn't we just use the wafer itself? That's called wafer scale integration. So that was an idea that was kicking around. Amdahl tried to do it with Trinity Corporation, and that crashed and burned. You know, our aerospace company did one, but I thought that idea would never come back. There's a startup company that's looking at a modern version of wafer scale integration. So all these ideas that didn't work for general purpose computing are being reevaluated for domain-specific architectures, and it's going to be very exciting to see how these all work. And the analog design, there's a startup that's trying to do multiplies via analog rather than digital multiplies, for example. So, and we'll see how these things all work out. So some things that have been, I don't know, either confusion or purposefully misleading is, well, TPUs are just ASICs, so they're not fully programmable. That's a thing that people say. So ASICs is application-specific integrated circuit. It's just kind of, you're using kind of non-Intel capable engineers are using CAD flows that are simpler than the really low-level stuff. But you're building a custom chip, and it can be programmable despite it saying application specific. So it's programmable. There's software is a good idea. We're trying to guess the way the world's going to be and how to get there, and so they try to be flexible enough, but it's domain specific. It's not going to be good probably for scientific computing, even though it's great hopefully for machine learning. And the balance, how much should you wire down, how much you should be flexible. So, you know, for architects, the TPU is really a coprocessor where it's controlled by the host, but the TPU v2 and future generations are really independent computers that fetch their own instruction sets, and they're used for research and production. Okay, now we're getting ready. So Google got Inference working, deployed it. They were happy with that. Okay, let's take on the next big task, training. So what should we build? Should we build it as a cluster, or should we build a dedicated supercomputer? And the cluster would work fine. That's what happened with the TPU. So it's an accelerator into a host, and you could just collect the hosts together using InfiniBand or something like that, and you have a cluster. That's a standard thing to do. That's exactly what Google did for Inference for AlphaGo. It had a cluster of 64 GPUs. The decision instead was to build a large supercomputer. And why? Because training of these production apps on a single chip could take weeks to months. And the conventional wisdom was the bigger data sets, the bigger hardware led to breakthroughs. And recently the OpenAI guys talked about that, and that factors of 10 every year. Well, that was what the bet. So we're going to build a supercomputer rather than a coprocessor chip that you can cluster together. And that was what decided to do. It's not the only way to do it. So what is a supercomputer? Supercomputer has the compute, which a lot of times they use even the same chips that you'd see in servers in that, and often the same memory or some variations, and then the interconnect. The interconnect is the big difference. They're not using standard data center networking. So the two generations that have been announced in, I think, 2017 and 18, I guess, are TPU v2 and v3. Those are the boards. Each of them have 4 chips, and you can tell, well, what you can't quite tell is the one on the left, TPU v2, has a big, you're looking from the top, but there's a very tall stack to do the air cooling, and the one on the right is liquid cooled. So it can cool, it's not tall, but there's liquid going through it to cool it off. So can get burned. It's much more efficient to use liquid cooling than to use air cooling, not surprisingly. The thing to the right there, that's the supercomputer for V2, which has 256 chips. And the one at the bottom is the V3 supercomputer, which has 1,024 chips. So are these things useful? So here's a paper that was presented at NIPS. And you can make, it's pretty small font, but I copied the table from it, and then I plotted it over there to the left. And that's showing kind of classically what you do with a supercomputer or multiprocessor. You show a scale-up curve. What happens is you increase the number of chips. And it talks about 3 things in this paper: batch size, the optimizer that's run when you're doing the training and you're doing the cascading descent, and the accuracy of the results. And that's plotted there. So the red one is the TPU with the Lars optimizer, and the blue one is the TPU V2 with the standard optimizer. And you can see they got a difference by changing optimizers. And then the TPU V3 starts off where that one ends and goes up to 1,000 chips, and it's pretty straight. So this is an example, and they went from, what's it say? It was 7 hours on 4 TPU V2 chips to 2 minutes on 1,024 chips, and the batch size is in the thousands. I mean, the biggest batch size was 65,000 things. All right, so that was, so we built the supercomputer. It's got its own custom network. Typically, that's what a supercomputer typically has, is a custom network versus a standard network. And designed to go very high scale. With each generation, it went bigger. Now, what about revisiting computer arithmetic? So the TPU used 8-bit ints and supported 16 bits. And training has almost always been done in floating point. And this is a thing that architects don't quite get about it. If I explain the quality score or accuracy score, you can have a little bit of flexibility in that, but that's lowering the quality is not popular for machine learning people. I could think of it, I built a computer, and it's really fast, but it gets the wrong answer. That's kind of how machine learning people think of you sacrificing it. So a 1% drop in quality is like, for them getting the wrong answer. They may spend 6 months of their life improving the quality score by 1%, and you're just going to throw it away so it can go faster. That doesn't win friends and influence people. Another way to think of it, if you're a company that's serving things to 1 billion people, that could mean millions of people have a bad experience, or if it's tied to income, a loss of income because it doesn't work well for them. So quality score, until machine learning works tremendously better, I don't think people are going to want to sacrifice quality score for that. So it pretty much has to be in floating point. There are research papers that I see, at least in computer architecture schools, that says, hey, we trained this one, but I don't know if that's going to. But usually the paper sacrifices quality a little bit to be able to train it in integers instead of floating point. So in practice, training is in 32-bit floating point, but there's no need for 64-bit floating point. But that, to NVIDIA's good fortune, or the GPU, AMD's good fortune, they're really good at 32-bit floating point, so it worked really well. But the question then, now, does it require 32-bit? You don't need more to get away with less. And kind of the answer is, you need it sometimes, but not everywhere. So, our colleague at Berkeley, Velvo Khan, invented the IEEE floating point, and that's the first two are the 32-bit version of the 4-bit and the 16-bit version of the format. So Google played around with that in the design of it and said, we wanted to get a narrow one because we could save hardware and energy. Is the IEEE format the right thing for machine learning? And they came to the conclusion it was the wrong thing to do. You see, there's not very many exponent bits, lots of mantissa bits. The IEEE floating point is a lot about accuracy, and almost any paper you read about machine learning says accuracy doesn't matter as much as other things. So Google shifted the exponent. Remember, we do those little tiny weight updates? If you need a bigger exponent so they don't go to 0. So the exponent, in this case, is 8 bits of exponent, but 7 bits of mantissa is good enough. So you can do that as the inputs to your multiplier. You can do 16-bit in what's called the brain format, and that works pretty well. And the reason people care about this is most of the area of is the multiplier, not the adder. It doesn't multiply add, but most of it's the area. It goes up to the square of the size of the mantissa. So if I square 23 bits or 10 bits or 7 bits, you can see that these factors here. So it's shifting the exponent cuts the area and cuts the energy in half. There's been a subsequent study of using standard IEEE format, and to make it work, because your exponent is not as wide, you're worried about some of those little tiny upgrades going to 0. So you have to do some extra work by the software to make sure those things don't go to 0. It's called loss scaling. So it was not. This is one of those rare things. It's actually easier for the software and more hardware efficient and more energy efficient to change the floating point arithmetic, violate the IEEE floating point standard because it's domain specific. You can think of it as a domain specific computer arithmetic. Okay, so just a little bit I can say about TPU. It's connected over PCI bus to the host. This is V2. That's the board. It's available in Google Cloud if you want to try and use it. The chip itself, instead of having one tensor core like we did in TPU V1, it was a better design to put 2 of them on a chip. You can make 2 of them more efficient, a little bit faster, because global wires don't scale as well. It's got a vector unit as well as the matrix unit. Most of the work is done in a 32-bit float. It's a smaller matrix unit. Before it was 256 by 256 8-bit. This is 128 by 128, but the inputs are brain float input and they accumulate in IEEE. So each cell is much more complicated, but there's 1/4 as many per tensor core. That's another picture of the pod. This is the VP pod that was May 2017 when it was announced. And you see this kind of relentless progress here. The first one was 1 chip. The next one's for the 2 boards. And kind of remarkably, the TPU V2 is 11.5 petaflops with 4 terabytes of high bandwidth memory. So a problem with TPU V1 is they use that standard DDR, so everything was memory bound. HBM is where you have DRAMs on an interposer chip next to the CPU, so not a lot of capacity, but tremendous memory bandwidth that basically all the accelerators are using. And the next generation is more than 100 petaflops. So how much is 100 petaflops? If you think of it as a supercomputer, and you go at the top 500, they're doing LinPack, and the peak performance of like the 4th one, say, is maybe 125 petaflops. This is doing 16 and 32-bit, running production applications. This is just the peak performance, not the delivered performance, but to give you an idea what that's like. And Google's not just building, it's not just a single supercomputer. It's not just one TPU V2 supercomputer and one TPU V3. There's lots of them, right? So that's a lot of computing. So how do we measure performance? One of the problems with our first generation TPU paper is we're using production applications. So nobody else, Google can't share their production applications. So how are we going to measure performance? When we can measure performance, we can make progress. So that problem surfaced about a year and a half ago, and we decided we needed to have something like spec was for CPUs for machine learning. And that led to MLPerf. It's got, I think, 30 some companies and 7 universities getting together to agree what's a fair way to benchmark programs. So kind of the one slide, I said spec for machine learning. They want to be quickly able to change it because machine learning is fastly changing. We want it to work for both researchers and industry. The way we make sure there's no cheating is to share everything so we can reproduce results. Try to be representative workloads, but keep it affordable so that everybody can do it. The 0.5 was published in December. There were 7 benchmarks. NVIDIA vetted 6 of 7, Google 3 out of 7, Intel 1 out of 7. So this is like the first draft of this. It exposed a lot of difficulties in doing this for all the companies. It's much more work than they thought. Google and NVIDIA in particular and Google showed this big scaling, and the next deadline is going to be next May. I think hopefully there'll be more submissions. They've also figured out some of the weaknesses in MLPerf that made it harder to scale up. And that's for training, it was May, and then they're going to do the first version of the inference benchmark in June. So training was easier to benchmark than inference, even though inference is easier to do. So that'll come out in June. So wrapping these things up, open question, what's the best architecture? Who knows the best architecture is? That's what makes it exciting times for computer architects. Everybody's got their own pet way to do this, and they're all making bets. And in computer architecture, when we make bets, that means hundreds of millions of dollars are being bet on our ideas, right? And how do we figure out who wins? The people who survive in the marketplace. So hundreds of millions of dollars are going to be invested in things that aren't going to work out as well, and there's going to be a couple that do, and that's kind of, that's the name of the game. Software probably matters more than hardware. So this is, software is king. This is a sad but true fact for computer architects. Historically, when the VLIW stuff, the multi-flow compiler was a really important artifact. And usually compilers take a while before they work well, so that's going to be a challenge. How small can arithmetic be? For inference, people are talking about 1-bit inference, right? Does training, how much flexibility do we have in training? Sparsity is really going to matter. How much does it matter? Can we use a lot more weights? There's some results like mixture of experts where they have tremendously more weights but don't access them all the time. How do we support that? And what about batch size? You'll hear about that. Batch size being low when you're doing inference and there's response time, that kind of makes sense. New inputs come in and you get the result quickly. The batch size probably should be small, but training doesn't look that way. So, this is a recent paper that came out at Google and it's on arXiv, and it's eye-opening for architects. So there's been a lot of folklore about batch size and accuracy and stuff like that. So my colleagues at Google really went into it very carefully, including figuring out the right optimizer, because you have to play with both. For a given error rate, you have to look at the optimizer you're using, and sometimes you have to change it. But on this log scale, this is the number of steps you have to take. So you want to get to fewer steps, and as you increase the batch size, what they found was this repeated pattern. For a first step out of batch size, you get a linear return. So if you double the batch size, it goes twice as fast, or you cut the number of steps in half. And then there's this area of diminishing returns, and then there's a size of batch size that pretty much, you don't get any benefit at all. You double the batch size, and it goes no faster. So this means a lot to computer architects because can you fit all the weights on your chip or not? Or do you have to go to other chips, or do you have to go to DRAM? And so for these results, the knee of the curve there, where you get into the diminishing returns, is for the convolutional neural network in the work. That's a batch size of 512. I think for the transformer, which is like an RNN, I think the batch size there is 2 to the 10th, so 1024. And then for the CNN on the right, this more complicated one, the batch size is 2 to the 14th, or 16,000, right? So looks like right now, the way algorithms are, big batch sizes get you really, you're getting it's kind of easy, kind of a computer architecture. Throughput is easy. You can put more things in. Latency is really hard. So if I can just get more throughput with a bigger batch size, that makes these things makes it easier for computer architects, provided you can handle bigger batch sizes. So, we're at this crisis, danger, opportunity, the end of Moore's Law. That's still, technology's going to get a little better, but much more slowly than in the past. The end of Dennard scaling. The problems that companies have had. Global Foundries gave up on 7 nanometer. Intel's been stuck in 10 nanometer for many years. At the same time, there's this opportunity, the revolution in machine learning. And the ironic thing is, right when we need Moore's Law, it's going away. Right when there's this factors of 10 thirst for computing, we're in this desert. And with that, but that's the bad news. The good news is for computer architects, huge number of opportunities, and that's why John and I say we're in a golden age. Okay, with that, I'm ready for questions.
That we don't run around this aisle right here.
We just need the first question. Great.
What's your take on applied quantum computing?
Yeah, quantum computing. I left that slide out. So I've given this. I actually I happily pass along the torch to Hinton and Baggio and LeCun, so that all the paparazzi will follow them around. But as a result of giving the Turing Award, you're kind of Turing. So I gave 35 talks last year. Right? Wow. But so I get the question when I talk about this data and about quantum computing. So recently, there have been 2 publications with people involved in quantum computing kind of giving a cautionary tale. And basically, it's not right around the corner. There was a workshop that CRA presented, and their first line is, we haven't identified a single application that is likely to run in the next 10 years where it will be faster than quantum computing. I mean, it'll be faster than traditional computing. They don't have a single killer app. There's no killer apps. And so kind of first item in the agenda is find that killer app, right? Given how well it's likely to work. So, more than 10 years out, they're optimistic. But if there's no practical results for decades, that may not match kind of what you read in the newspapers today. And there was also a similar work by the National Academy of Engineering, which also kind of gave that cautionary thing. It's potentially revolutionary, but it's probably at least 10 years away before the practical impact of it. And I'm delighted because I was hoping I would retire before quantum computing came along, so I didn't have to learn quantum computing, so I'm safe. You guys may be in trouble, but a question?
Hi. My question is related to a domain-specific architecture. You're talking about bfloat, where you're reducing that from 32-bit to 16. Now, in real time, we are getting a data either in float or a double. So are we losing any information when we are doing a machine learning? Or
the question has about numeric precision and accuracy, right? And are we losing information? And yes, we're losing information. Kind of the miracle of deep neural networks, which we don't fully understand, is that it appears to be, every time you run it, you get a little bit different answer, so they do lots of runs. And they're not, if we were doing supercomputing, and every time you ran a program in a supercomputer, and you had a bottom line answer, and that number changed a little bit in the last few percent, something's wrong, right? This is broken. It's got to get the same answer every time. That's not the way machine learning works. That works fine. We're kind of imitating intelligence, right? And so we're doing much higher level functions rather than calculating something to very high accuracy. So I'm not a machine learning expert, but nobody has ever asked for anything more than 32-bit, and many people are exploring narrower things. So I think it's safe.
Question about general architectures, including wide area network architectures.
Including what?
Wide area. And
wide area network?
Right. So you've talked about the architectures that you're building and that Google are building for use in their data centers. Now, Google is also building machine learning support for use in handsets.
Right.
Do you see any place for a third location for that processing to be run? In other words, a scale of processor where it is, for example, as the 5G people are trying to market, something located at the base of towers, or basically some intermediate location that's neither the tiny handset that's in people's pockets nor the big, enormously large-scale supercomputer.
Yeah, so keep in mind, there's perceived to be lots of money to be made, so people are trying everything, right? And so I personally believe the future is at the cloud and the edge, but there are people who are investigating computing at the base station. And that it would depend, well, certainly it makes tremendous sense. Most of the startups are building inference chips for the edge, for IoT. That's for most of and that makes tremendous sense. Kind of the question for training is, are there benefits of collecting all that data together from one place from lots of users? Do you train it better in the data center? And there's even people who argue you should try and train on the edge devices as well, but that's going to be one of these trade-offs. And then is there some kind of knee of the curve? Would you get some of the benefits at the base station for things? And presumably that'll have to do with the application. If self-driving cars needed to have something, if they're using 5G and coordinating somehow with very high response time, maybe I could see that. I could see that. But you know, right now there's tremendous excitement about the market, and people are investigating everything. So I'm sure that's going to be one of the places people do. Okay?
Hi, I'm Gary with Intel. I wanted to ask you, do you think domain-specific architectures are going to be targeting different applications with different techniques, whether it's speech or vision or other? Because you didn't really specifically go into those fine-grained applications.
Yeah, so there's certainly going to be other applications that people don't use deep learning to do, like compression or security and stuff like that. I mean, as far as we know, the only way to do it is special purpose architectures. The beauty of deep neural networks is it works on lots of things, right? It helps with image recognitions. It helps with language translation. It helps with you know, ranking searches on the web page. It's kind of a general purpose thing that works on a surprising number of applications. So that's why there's all the excitement about it. But I'm sure there'll be special purpose other things. If we want things to get faster, more energy efficient, my guess is we'll see kind of a standard CPU with lots of accelerators that are dedicated to these narrower areas. It's going to be a lot harder to build hardware and software this way, but that's all, you know, that's all we know what to do.
Thank you. I also look forward to more recent CPUs up there in your presentation. Thank you.
Oh, yeah. I look forward to being able to publish more recent papers. Yeah.
Hello, I'm Dmitry from Apple. So I think the TensorFlow and NumPy can be looked more like a general purpose compute engine, like where you, instead of just writing loops, you use just these tensor operations to do the computations. And if you look at this problem this way, then probably you can think of this deep learning hardware. It's not really a domain-specific hardware. It's just a different way of doing a general purpose computation. And I wonder if you probably see it in a sense that way, or maybe if you foresee some sort of standard like OpenCL or CUDA for GPU, but like some sort of TensorFlow like for these general purpose machine learning applications.
Well, you know, these are kind of data flowish languages which hadn't caught on. So it depends on your perspective. At 50,000 feet, it's still, you know, a somewhat standard programming language and somewhat standard hardware. Compared to the past, it's radical, right? We're not writing in C or C++. We're not writing, you know, cache-based architecture. So it depends on your perspective.
Well, maybe then more specific. Do you foresee like any sort of standard, like appearing like OpenCL, but
well, standards, well, the question is, what are these things like? What is TensorFlow like? Is it like scripting languages, where every few years a new one comes along, or is it like programming languages that last for decades, right? People are still writing C 40 years later, and C++ 20 years later. I think it's more like scripting languages. I think people are finding new ways to be more productive and coming out with new ones frequently. So I think it's going to be, I expect there'll be much more innovation in these ML platforms, would be my guess.
Okay, thank you.
Mm-hmm. One more? Yeah, okay.
Hi. You mentioned the old multi-flow compiler as an artifact, and having worked for a couple of their competitors, I'm just curious what point you were trying to make.
Oh, it's just that if you think about the VLIW architecture, the key piece of technology was the compiler. It wasn't the hardware that was built or the architecture, it was the compiler. And the make or break of it was how well the compiler worked. So that's an example, as we look back historically, that hopefully multi-flow put all its resources in the compiler rather than in the hardware design, because that's what they needed to survive. And you know, and Intel and HP with the Itanium and their compilers didn't quite work well enough to deliver on that bet. So the question is that what we're to survive? Are the winners not going to be the architectures? Is it going to be the ones with the best compiler technology? You know, that would be, or the best libraries or something like that. But you know, like I don't know who's going to win. I know in 10 years, we'll look back and say, obviously they were going to win. You know, we'll look at these reasons, that's why. But right now, it's hard to figure that out. But it might be the compilers. I got to say, I was a little disappointed because I was involved in the MLPerf getting started. And one of the reasons I wanted to get it started was for the startups to use it, and so we could kind of see what everybody's got. And so far, the startups haven't participated. So why? Was it chip problems, or maybe their software stack wasn't ready? I don't know. But I'm hopeful that, you know, for the next time, we'll see some of the startups in there and see how they work. But, you know, it's going to be interesting to see how they do, and, you know, if they don't do well, why. Okay.
All right, let's thank Dave one more time.
Okay.